Okay, so this video is going to be the introduction to topic 7.2, nuclear reactions. So this topic kind of builds on the topics we learned in 7.1, where we talked about things like, models of the atom, half-life, radioactive decay, stuff like that. And so nuclear reactions is a really interesting topic, and there's different types of nuclear reactions that we're going to talk about, both artificial, meaning man-made, and natural. And some of those include things like radioactive decay, which we've already talked about radioactive decay in 7.1 when we talked about, alpha decay, gamma, beta, beta plus, beta minus. And you have radioactive decay when you have basically an atom that has an unstable nucleus because there's an imbalance between the strong nuclear force and the electromagnetic force holding everything together. And so radioactive decay is one example of a nuclear reaction. Now there's other examples of nuclear reactions, and some of these you might have heard of. And so in this unit we're going to talk about artificial transmutation, which has some really interesting applications in the medical and industrial field that we can talk about later. Nuclear fusion, which naturally powers our sun. Our sun gets its energy from nuclear fusion. And if you've ever heard of a hydrogen bomb or an H-bomb, the energy for that type of bomb primarily comes from nuclear fusion. And then you have nuclear fission, which most nuclear weapons these days use nuclear fission. Some of the more powerful ones use fusion, like I said before. But most people, when they think of nuclear power plants, they're thinking of power generated by nuclear fission. Okay, and so these are all examples of nuclear reactions. So, what is a nuclear reaction? Well, simply put, a nuclear reaction is a process in which a particular nucleus changes into one or more different nuclei. Okay, so remember when we talk about a nucleus, we're talking about that small, dense, positively charged center of the atom. And remember, nuclei is just the plural of nucleus. Now, we've only seen one type of nuclear reaction before in any detail, radioactive decay. Remember, there's different types of radioactive decay, but we did have some practice using a periodic table to help us write nuclear decay equations. Okay, and so we're going to start off by talking about artificial transmutation, and as we progress through the unit, we'll later on talk about fission and fusion. Okay, but they all have the similarity to them. Now, artificial transmutation, the term artificial basically means man-made. Now, there is natural transmutation, but artificial transmutation is transmutation that is man-made transmutation. Now, of course, that doesn't help you if you don't know what transmutation is. Okay, so transmutation is a vocabulary term that you should know. And basically, when we talk about transmutation in this context, we're basically talking about one element changing into another element. Okay, now we've seen that before in radioactive decay. For example, something under, you have one atom, one type of element, and it undergoes, let's say, alpha decay, and then you end up with a completely different atom on the other side of the equation. That is an example of transmutation. Artificial transmutation happens when basically we as humans artificially cause transmutation to happen. Now, typically the way we do that, in very simplistic terms, is we take a sample of our target atoms or our target nuclei, and well, we shoot stuff at it. Okay. In the notes it says that when a nucleus is bombarded with a nucleon, an alpha particle or another small nucleus, bombarded is just a fancy way of saying we shoot stuff at other stuff, and it can cause the original stuff to change into a different element. Okay, so typically you see artificial transmutation, like I said, you take a sample of some type of atom and you shoot protons or neutrons or alpha particles or some other type of particles at those atoms, and through some type of nuclear process you end up with a different product. Now, oddly enough, the person to discover the first artificial transmutation is actually somebody we've talked about before, and that is Rutherford of the Rutherford Model. Okay, remember, Rutherford came up with the first nuclear model of the atom. We talked about that in 7.1. The first nuclear model of the atom as a result of the Geiger-Marsden experiment, where they, did the whole shooting alpha particles at gold foil and whatnot. Okay, and so I guess, Rutherford liked alpha particles so much that he tested bombarding other things with alpha particles. And basically, what he found, if I go the next slide, is if you take alpha particles and you shoot them at nitrogen atoms, you get a product that is actually oxygen. Okay, and so this right here is a pictorial representation of this nuclear reaction equation. And so this is a nuclear reaction equation right here. We've seen similar type of equations before when we talked about radioactive decay. They kind of look like chemical equations, but this is a nuclear reaction equation for artificial transmutation. And what we have on the left side, that is the reactant side, is we see that we start with nitrogen 14, we hit it with alpha particles, okay, and as a product we end up with oxygen 17, plus 1 proton. Okay, now you might ask, well, how do we shoot alpha particles at nitrogen? Do we have like an alpha particle gun or something like that? Well, basically, we can just take a sample of something that is radioactive that's emitting alpha particles, and if we put it close enough to the nitrogen atoms, then it acts, as a source of alpha particles to cause this artificial transmutation. Now, again, this is artificial transmutation in the sense that we are artificially causing this to happen by getting a sample of nitrogen and bombarding it with alpha particles. This is kind of a cool thing if you think about it, because for hundreds and thousands of years, people have been trying to change one element to another element. And now I'm showing you that it's actually possible. You can turn nitrogen into oxygen if you know what to hit it with. So that's kind of a cool thing. Pause it there if you need to look at that some more. Another type of artificial transmutation I want to show you is actually even cooler, I think. It turns out that if you take mercury 200 and you bombard it with high energy protons, you can actually produce gold as a product, plus some alpha particles as products as well. In other words, I'm telling you that you can take mercury and turn it into gold. Okay, that's modern day alchemy right there, right? Making gold from something else. That's awesome. Now, the issue with that is in order for this reaction to happen, not only do you have to hit the mercury nucleus with the proton, but this proton has to have a lot of energy. Okay, and in order to get protons that have that much energy, you have to use a particle accelerator. And in order to power that particle accelerator, it takes a lot of money to produce the electricity to run that particle accelerator, and the gold that you get out doesn't make it worth it. In other words, okay, so if you get like $1 of gold out, it could cost like thousands of dollars to produce that amount of gold. I'm just making those numbers up, but it's not like this is not gonna make these people super rich. But this is in fact a possible nuclear reaction, which is kind of cool. Okay, so that is another example of artificial transmutation. I will tell you, by the way, as you're looking at the second artificial transmutation equation, notice that it's different from radioactive decay. One of the key differences between artificial transmutation and radioactive decay is radioactive decay, you always start with only one reactant. You always have one unstable nucleus, okay, on the left side, and it always decays into one daughter nucleus plus a type of radiation particle. Notice in artificial transmutation, we have two things on the left. Now, that doesn't mean if you have two things on the left, it's automatically artificial transmutation. Because as we'll see, fission and fusion can also have two things on the left. But each type of nuclear reaction, you need to be able to recognize based off of context clues. Because sometimes you'll have questions on the IB exam asking you to do so. Okay, pause it there if you need to look at that reaction some more. Okay, now I will also tell you, just because I don't think it's in the notes, other examples of using artificial transmutation is it can be used to create radioisotopes for medical purposes. I said that before. You can also bombard radioactive materials that come out of nuclear reactors that are really dangerous, and bombarding them with certain particles can turn them into something, let's say, less radioactive. Okay, so you can make the waste products from a nuclear power plant safer in a way by doing that. Okay, so there's a lot of interesting applications of artificial transmutation. Okay, before we move on, I think we've talked about this before, but I do want to remind you about the nuclear notation symbols for protons, neutrons, and radioactive decay particles. Those are all things you would be expected to know. Remember, a proton is written like this in nuclear notation. A neutron is 1, 0, n. Okay, remember the top left number is the mass number. Okay, and the bottom left number is the atomic number. That's the number of protons, and the mass number is the number of nucleons. Okay, so a proton is 1 nucleon and 1 proton, so that's why it's 1, 1. And then you have the 3 types of, or I guess 4 types of radioactive decay particles. You have alpha, beta. Technically, you have 2 types of beta. You've got beta minus, and you have beta plus, and then you have gamma. And this is all stuff you should be familiar with, but remember, an alpha particle is a helium nucleus. A beta particle is an electron. A beta minus particle is an electron. A beta plus particle is what's called a positron. That is a positive electron, and we'll talk more about that in 7.3 actually, because that's an example of antimatter. And then gamma is just 0, 0. It's not super common to see gamma. The symbol for that looks like a fancy looking Y. Okay, so just to kind of recap those things. Now, I did have somebody ask me a while back, why do we call, if an alpha is helium-4, why not just call it helium-4? Why call it alpha? Well, nowadays, of course, we could call it helium-4, but at the time these radiation particles were discovered, this is like the late 1800s, we didn't even know the nucleus existed, much less, know about, different types of atoms and whatnot. And so it was only through later investigation that we discovered, hey, this type of radiation we've been studying for like 30 years, guess what? It's actually a helium nucleus. Okay, and so that's why we came up with the names alpha, beta, gamma. That's like A, B, C in the Greek alphabet. We came up with those first and then filled in the blanks, years and years later. Okay, so pause there if you need to review any of that. Okay. Now, this is a type of another type of nuclear reaction equation, and we've seen this before. This is all just review. I just wanted to remind you, this is actually a nuclear reaction equation showing the alpha decay of polonium-214 as it turns into lead-210. I do want to remind you that solving problems with nuclear reaction equations can be very easy as long as you understand that the mass number has to be the same on both sides of the equation. Thinking of this this arrow as an equal sign, and the atomic number also has to be the same on both sides of the equation. In other words, what I'm saying is 214 has to equal 210 plus 4. Okay, and 84 has to equal 82 plus 2. So for example, if you had a problem given to you where, let's say I didn't give you this, and I didn't give you this, and I asked you to fill in those blanks, you should be able to do that using basic math. Okay, and again, we talked about that in 7.1, but I just want to refresh that concept, and that's true whether it's radioactive decay or whether it's any other type of nuclear reaction equation. Okay, so that applies throughout this unit. Okay, so let's do some quick examples. Okay, the examples you're about to see are all from past IB exams. This question says, in a laboratory when aluminum nuclei are bombarded with alpha particles, the following reaction may take place. And then it asks you, basically, this reaction is an example of what? Now, the options are, fission, radioactive decay, fusion, and artificial transmutation. Okay, so see if you can use the context clues that we've talked about to answer this question. Okay, so the answer to this question is D, artificial transmutation. Now, if you're, using process of elimination, you can eliminate C right away. You can tell it's not radioactive decay because there's 2 things on the left side. Radioactive decay only has 1. Now, at this point, we haven't talked about fission and fusion, but as we do, you'll see fission and fusion both have context clues that are unique to them, where you should immediately recognize fission and fusion when you see it. Okay, artificial transmutation, again, you typically have some type of particle like a proton, neutron, or alpha particle hitting one type of atom and then producing another atom. Okay, that's like the definition of artificial transmutation. Okay, so pause it there if you need to review that. And then just to take a look at a few more things, take a look at this example here. It says when a high-energy alpha particle collides with an aluminum-27 nucleus, a nucleus of phosphorus may be produced. Which of the following equations correctly shows this transmutation? Now, this is not the best example to give you because I think it's the same equation as we saw before, but let's pretend we hadn't seen that. Now, if you use process of elimination, which is great for multiple choice questions, you can eliminate some answer choices right away. For example, they tell you that there is an alpha particle colliding with the aluminum. Okay, that means one of the reactants should be an alpha particle. Helium has an atomic number of 2, not 1. Atomic number of 1 would be hydrogen. So you can eliminate C and D right away because that's not even right for helium right there. Okay, that's out and that's out. Now between A and B, the way you would do that is to recognize that, okay, the only difference is here you have, N10, and here you have P10. This is a neutron, this is a proton, but the problem is, hopefully you spotted it, that's not the correct symbol for a proton. Proton should be P11. So B is not the correct answer, and the answer should be A. And again, that's based off of a previous IB question. Sometimes IB questions can be very challenging. Sometimes they can be very straightforward, like this is an example of a straightforward IB question. Okay, pause it there if you need to look at that some more. Okay, and just one more quick thing before we get to the end of this video. As we move on in this unit, what we're going to do is we're going to introduce different units of mass. Now, all throughout IB Physics 1, we've talked about the unit of mass, that is the kilogram. And we've used the kilogram basically non-stop since we learned about mass back in forces. Okay, the kilogram is the SI unit for mass. It's one of the 7 fundamental base units in the SI system. However, there's an issue with the kilogram, and it's not really that big of an issue. But the issue is when you're talking about, atomic sizes and nucleus sizes, the numbers are so tiny that's kind of, annoying to use numbers so small. For example, the mass of a proton is approximately 1.673 times 10 to the negative 27 kilograms. Now, there's nothing wrong with using that, it's a really small number. And so it's convenient to have units of mass that are more suitable for this scale. And so what we're going to do is we're going to introduce 2 new units of mass. Number 1, you have the kilogram. Number 2, we have what is called the unified atomic mass unit. For that we write U. Now, if you've never heard of that before, if you've taken chemistry, which hopefully all of you have, you might have seen this differently. You might have seen it written as AMU for atomic mass unit. Okay, when I learned about this, we call it AMU. U is just what the IB calls it for physics. It's the same thing. Okay, so you have the unified atomic mass unit. In unified atomic mass units, the mass of a proton is 1.007276 U, or AMU, whatever you prefer to write, but U is probably better in this class. Now, by the way, all these numbers you would be given on the IB exam, so you don't necessarily need to memorize any of them. I will say I would highly recommend you take a picture or you write these down in your notes, just because you are going to be using these a lot, and it would be good to have access to them. Do keep in mind on any like test situation like the IB exam, you would have access to everything I have up here, all of these numbers. Okay, so just keep that in mind. I would definitely write it down for now though. Now the third unit of mass looks a little funky, and it will make complete sense why it's a unit of mass later, but this is what it is. We have M, E, V, and then notice we have C to the power negative 2. Remember, anytime you have a negative exponent, the way you say that is per. Kind of like how meters per second squared we write like this. Okay, negative exponent means that thing is on the bottom, and when it's on the bottom and you're dividing, you say per. So the way we pronounce this is MEV per C squared. Okay, Now, you might be asking yourself, what the heck is a MeV per c squared? Well, an MeV is a unit of energy. Okay, we've talked about EVs before. EV by itself is a small unit of energy called an electron volt. And we talked about this last year, but 1 electron volt is equal to 1.6 times 10 to the negative 19 joules of energy. It's just a very small amount of energy. 1 MeV is basically just that, but it's the mega version of that. So mega electron volt. So it's basically 1,000,000 times this number, because mega is 10 to the power 6. Okay, so that's what MeV is. MeV is a unit of energy. Okay, it's very important that you realize MeV per c squared, even if you don't understand why, MeV per c squared is a unit of mass. Okay, don't confuse MeV, which is a unit of energy, and MeV squared, which is a unit of mass. Now, again, I haven't talked about why it's a unit of mass. It'll make complete sense later on, but that is in fact a unit of mass. Okay, one more thing I just want to add. I didn't talk about this before, but a unified atomic mass unit has a definition. It's always good to know the definitions of things because sometimes you're just straight up asked for definitions. Okay, so definitions are definitely important. But the main takeaway from the slide is that there's 3 different units of mass. You have to be familiar with all 3 and recognize each of these as a different unit of mass. You've got the kilogram unified atomic mass unit and MeV per c squared. Okay, please pause there, write down anything you think is important, add it to your notes. Okay, especially the definition of unified atomic mass unit, which is 1/12 the mass of a neutral carbon-12 atom. Okay, so let's take a look at a few more slides and then we will be done. Actually, just one more example. Okay, again, from previous IB exam, look at this. It's a definition question. Definitions are important. The question says the unified atomic mass unit is defined as, this is one of those questions that's super easy as long as you happen to know the definition. So I'm going to reiterate throughout this school year, definitions are important. As we go on later on, we'll spend time doing vocabulary review so that you make sure you get your definitions down. Because if you get stuck on a complicated calculation problem, that's understandable. But if you don't know the definition of something and you miss a point because of that on a test, that's just kind of silly. That's something you can easily prepare for as long as you have the definitions. Okay, so remember, definitions are important. Okay, easy answer as long as you happen to know it. Okay, now we are going to leave off with just one more thought, and we'll talk more about this in the next video. So I just want to leave you with this thought here. Helium-4, okay, so a helium-4 atom, basically, or I should say helium-4 nucleus, is you've got 2 protons and you've got 2 neutrons. And I'm just going to state this as a fact without any explanation. But if you read this, if you compare the mass of a helium-4 atom to the mass of 2 protons plus the mass of 2 neutrons, these 2 numbers are not the same. Okay, so the last thing I want you to do in this video is I want you to find the difference in mass. We're going to write delta M. I want you to find the difference between the mass of a helium-4 atom, which I give you the mass right here, and the mass of 2 protons and 2 neutrons. I've given you the masses of 1 neutron and 1 proton right here. I want you to find that difference. Now, you might be asking yourself, why would they be different? Okay, basically what I'm telling you is if you take 2 protons and 2 neutrons, you weigh them, and then you put them together inside a nucleus, they don't weigh the same after they're inside a nucleus. That's what I'm telling you. And I'm not going to tell you why quite yet, because I want you to chew on that. It's kind of a weird concept. Okay, but I do want you to do this calculation. Okay, so pause it there, get a calculator while you're racking your brain over what the heck I'm talking about. Do this calculation. It should be a very small number. Okay, the difference between the mass of the atom and the mass of the 2 protons and 2 neutrons, it should be a very small difference, but it is not 0. Okay, so do that calculation. Pause it here. Okay, so record your answer. And then we will talk more about this concept in the next video. This is called mass defect. And it's a very interesting type of thing, and it's going to lead to even more interesting things later on. Okay, so chew on that. See if you can figure out why that might be. And I will see you guys, or I was going to say, I will see you guys in the next video. Please let me know if you have any questions.